So hello to all, how are you? Good evening. I hope all of you are well and doing good, my dear student. So let's start today's session. As today's session we are going to discuss, this is our lecture number 7. Today we are going to discuss life, okay, that is tool life and tool. In this lecture, we are going to cover topics like your tool failure, your mechanism, tool life equation, economics of material. Basically, GATE will ask a question on these topics, right? Now let's start. My dear, let's try to understand tool failure and tool mechanism first, right? Tool failure and tool mechanism first. So let's start now. Before that, let me draw the tool here. My dear, there will be a tool. Please try to understand, right? A tool. Here I am drawing the tool properly. You will get a proper idea. Now, as you can see, our tool. See here, right? This is the tool. Now, there will be two types of failure. One will be on the rake surface. My dear, this is the rake surface. Rake surface. Rake surface. Or we call it face off. On the rake surface, there will be a crater wear on the minimum on some minimum distance from the side cutting. Right. So a crater a crater is going to be reduces. This is a crater view. Got a crater view, right? A crater now, right? And there will be a wear just below the side cutting edge, usually on the flank, usually on the flank here, right? Little bit on the nose, and this here is known as this here is known as basically a flank wear, right? This wear is known as flank. This wear flank, right? Now the reason for the flank wear, right? This is the flank wear, the crater. Now the reason, right? The reason for the flank wear. Whenever the cutting velocity is slow, at low cutting speed, at low cutting speed, right? Flank wear will basically what happen at the low cutting speed. At low cutting speed, generally PUE, you know that at low cutting speed, right? PU built up edge formation will happen, and built up edge is what plastically deformed material. Plastically deformed material, right? Plastically deformed, okay, which is harder, which is harder. So when the plastically deformed material on the flank, then what happen? Scratches would, right? And on the rake surface, know that chip will flow on the rake surface. Chip will flow on the rake surface, right? Chip will flow on the rake surface. What is the chip which is flowing? Now, when the chip is flowing on the rake surface and the continuous chip is flowing, then what happen? After some point of time, okay, the temperature get increases and the material from the tool material from the tool side will diffuse the chip. So this will happen at high cutting speed, right? This will happen at high cutting, at high cutting speed, right? At high cutting speed. What happened? At high cutting speed, the temperature get increases and the material get diffused. Okay, material get diffused, get diffuses, okay, diffuse from tool to chip, right? A creator will get, a creator is going to be what produces, right? Material get diffuses from tool to chip, right? So this is the reason. I hope you understand. Okay, what is the basically what type of failure, my dear? These failure generally comes under the slow, right? Will come under what? Under the category of slow death. So let me write down, if whether you are talking about, whether you are talking about crater wear, whether you are talking about crater wear, crater wear occur due to high cutting speed, high cutting velocity, high cutting velocity, right? And if you are talking about, if you are talking about, let's say flank wear, right? So flank wear will occur due to low cutting speed, due to low cutting speed, right? Due to low cutting velocity or speed. My dear, we know the reason. My dear, we know the reason of the crater wear as well as the flank wear, so that we can control this factor, right? By manipulating the velocity. So that's why they comes under slow death, right? Slow death. The tool is slow death. Basically, they comes in a slow death category. They comes in the category of what? Slow death, right? They comes in the category of slow death. Basically, here your flank wear, right? Your flank wear affect the component component damage, right? Component damage. So it is very important to understand the wear mechanics of the flank wear, to understand the wear, okay, wear pattern of the flank wear. My dear, let me draw the flank wear, right? The wear versus the flank wear versus what? Time. The flank wear versus what? Time, my dear, right? The flank wear versus what? Time. So this is flank wear, right? Flank wear, or you can say scratch height, and this is what? This is a time. Now this wear, okay, we can obtain the graph of flank wear versus time like that. A curve initially, then there will be a, straight line, then after there will be a curve. So we are going to categorize these wear into three categories, into three, okay, into three type of wear. That is a primary wear zone. This is what? This is a primary wear zone, my dear, right? This is what? This is a secondary wear zone, and this one is tertiary wear. This is primary wear zone, this is secondary wear zone, and this is tertiary. My dear, in this wear you can understand that initially the wear rate is high. Initially the wear rate is high, right? Till you can see the wear rate is high. Okay, as time goes on, goes on, wear rate decreases, right? Wear rate what? Wear rate get decreases. Okay, so there is a curve. After some point of time, the wear rate will be constant, right? After, okay, some point of time, the wear rate again gradually increase. The wear rate again gradually increase, right? The wear rate again gradually increase. So this is a pattern of flank wear which will happen, right? So why basically let me talk about the primary wear, my dear. Primary wear basically the reason where the sharp cutting edge is quickly broken down and a finite wear length is stabilized, right? Initially the tip is very fine, and the tip is going to be quickly broken down and a finite wear length will be comes out, right? So this is a primary wear. Now in the secondary wear zone, when the finite wear length will stabilize at the tip, when the finite wear length is stabilized, then the wear rate become what? Uniform. So the reason where the wear progresses at a uniform rate, right? At a uniform rate. If you see the slope, right? If the slope, here the slope, here the angle is very small. The slope is constant. The slope is what? The slope is constant. Now let's talk about the tertiary. In tertiary wear zone, the reason where wear progresses at uniform increasing rate. The wear progresses at uniform. The wear progresses at a gradual increasing. Here you can see that wear here increases at gradual increase at gradual gradually increasing rate. Increasing rate in rate, right? Increases at gradually increases or wear progresses. I have to write that wear progresses, not wear. Here the wear progresses progresses at gradually increasing. Why? Because from the initially, in basically from the initially, tool is continuously doing cutting, so temperature goes on increasing. So in this tertiary region, the wear of the cutting tool has become sensitive to increase the tool temperature due to high wear length, right? So scientists generally don't recommend to go into the tertiary wear zone. So regrinding is recommended. So regrinding is recommended before before to enter in this, right? Before to enter in this. Okay, always remember this point, right? Always remember this point. Now let's move to understand the basically let's move to let's move to the Taylor's two life equation. This Taylor two life equation is very important from gate, right? From gate point of view, the Taylor's two life equation is very important. First of all, we have to try to understand two life criteria, right? First of all, we have to understand the two life criteria, right? Two life criteria, right? Tool life, write down tool life criteria. Tool life criteria, right? Criteria, tool life criteria. My dear, two life criteria can be defined as predetermined numeric, right? It is what? It is a predetermined value. Predetermined numerical value. Determined numerical value. It is what? It is a predetermined value. Once you know the value of the tool life, you are aware that up to that value we can use the tool, right? Predetermined numerical value of any type of tool deterioration which can be made. Now, this predetermined numerical value can be what? The actual cutting time to fail. It may be the actual cutting time fail. Actual cutting time, cutting time to fail, cutting time fail, right? Actual cutting time to fail. Second, volume of metal removed. Volume of metal volume of metal removed, right? Volume of metal removed, or it can be the number of parts produced. I mean, let's say I can use the tool up to 60 minutes or 50 minutes. This is what the predetermined numerical value. I can remove the material of 1000 cube material, then after tool is not useful for us, right? I can find out the predetermined numerical value, that is a number of parts produced. Number of parts produced. Number of parts produced. Right? Number of part produced. My dear, it may be, let's say you can produce, right, 20 parts. 20 parts. After producing 20 parts, the tool is not useful for us, right? The cutting speed, by telling the cutting speed, you can give the idea of tool life. Cutting speed for a given time, right? Cutting speed for a given time. For a given time, let's say you can say, sir, if the cutting speed is 60 meter per minute, then the tool life will be what? 90. So it is the tool life criteria. When you are using the tool at a cutting speed of 60 meter per minute, you can use the tool up to 90 minutes. So these are the predetermined numerical value. Then how can we find out that predetermined numerical value, my dear? The Taylor's tool life equation, basically this equation is p the power n equal to, right. This Taylor to life equation is based on flank wear, right? This based on flank wear. Here v is what? Let me write down, right? Let me write down. Here v is what, right? And here t is what? Here n is what? Here, my dear, let me write down. Here v is the cutting velocity. Here t is the time. Here n is the exponent, the constant. Here v is the cutting velocity. Cutting velocity, right? Cutting velocity. The cutting velocity must be meter per, right? T is the tool life corresponding to the cutting velocity, life, and that tool life must be, and is what? Tool exponent. And is what? It is the exponent depend on material. Is what? Exponent depend on material. Tool material, right? And C is what? The constant based on tool. Constant, constant based on based on tool, right? Constant based on tool. And work material, work material, work, right? Work material and cutting condition, and cutting condition, cutting cutting condition. Life equation, my dear, right? Remember this two life equation. I told you it will be based on your flank wear, right? It will be based on your flank wear, right? Here the value of n, right? The exponent n. Let's talk about the exponent. Let's talk about the exponent. Here, my dear, as I told you, the n can vary from material to material of the tool, right? So let's talk about value of exponent. Value of exponent, right? Value of exponent, that is what? N, right? Like for HSS, for HSS, right? N will be what? You have to remember the value of n. You just have to understand for HSS the value of n is 0.082, 0.2, right? 0.2. For carbide tool, for carbide tool, right? At least remember for the important tool material. For carbide tool, the value of n will be 0.2 to 0.4. For ceramic tool, my dear, for ceramic, the value of n will be 0.52, 2 point, right? So these are the value of n, right? These are the value of n. My dear, you have to understand one more very important relation in between the two life equations. What is that? Let me write down here. My dear, as we know that the power n equal to, take log on the both side. So log plus n log t equal to log, as usual it is a constant, let's say, or let's say k, right? N, t is k is constant, n is constant, right? Right. So I can write that minus log plus log c, right? Log c, and it is a log p. My dear, please equation, please see, and if you compare this, you can write that y equal to mx plus, right? You can write that y equal to mx plus c, my dear. So overall, the thing is that if you draw the curve in between, okay, log versus log t, the slope is what? Here the slope is negative, that is minus, means as the slope will be always be negative, means for HSS the value of n is what? The value of n is what? For the value of n for HSS very small, the slope is small. See here, right? For carbide the value of n increases, right? And for ceramic the value of again n. So I can write that it must be for HSS, it must be for carbide, and it must be for ceramic, right? It must be for ceramic, right? Ceramic. Understood? So this is the graph in between log V versus log T. I hope this point is crystal clear. Now let's move to the economics of metal cutting, my dear. Let's move to the economics of metal cutting. Now, economics of, before moving to the economics of metal, let me further discuss this relation. Again, what is the equation? You have seen equation is V t to the power n, right? Here t is the tool life, here t is the, right? Here is the, I can write that, I can write that t equal to by, right, by 1 by n. So here your tool life will depend not only on the machining condition, okay, workpiece and tool material, also on the cutting wheel. My dear, now I'm going to write extended modified, right? I'm going to write extended modified equation. Now let's try to understand this extended modified equation. Extended or modified Taylor equation. Extended or modified Taylor equation. Extended, extended or modified, or modified, right, Taylor's equation, right? Extended or modified Taylor's equation. Now what is that equation? The equation is pretty simple. Let me write down this equation. Equation is v2 to v, v to the power n, f to the power a to the power b equal to b and t, as usual same, is the d is the life, here f is, and d is depth of, right? It is a cutting velocity, cutting velocity, right? It is cutting velocity, and the unit be in meter per minute, right? T is the tool life, is the life, right? F is the feet, the unit per pass. D is the depth of cut, right? Depth of cut, and the unit must be, right? N, as you know, the exponent, as usual, AB are the constant, N is the exponent, right? A and B, A and C, basically are what are constant, right? So according to this condition, you can write that the Taylor's tool life equation. You can write the Taylor's tool life equation. The Taylor's tool life equation T equal to the power 1 by n divide by divide by right divide by p to the power by n f to the power a by n the power, right. Now when you compare the power, okay, then it was found that 1 by n is greater than a by n is greater than by, okay, it was found from the experiment, then it is greater. It means velocity affect more, okay, then after v, then after your depth of, so velocity will affect more the life, right. If you increase the feed by same amount, then feed will affect less compared to the compare if you compare to the cutting velocity. If you increase the depth of cut by same amount, then the tool life affect very less compared to the feed, right. So velocity affect more and depth of cut affect less. So I hope this this basic is clear. Now let's move to the economics of, right, economics of metal. So economics of metal cutting is what? Let me draw the curve. Okay, let me draw the curve. This is the cutting cost, right? And this is what? This is your cutting velocity, right? This is the basically cost per unit volume, right? On y-axis, cost per volume, unit volume, and on the x-axis there will be a cutting speed. There will be a cutting right there. Now there will be two types of cost. One is what? One is the cutting cost. So this is what this cutting cost might be. You can see this is what the cutting cutting. The green color will represent the cut. Now the next cost is your tooling cost, right? That is the cutting cost is me when you are cutting the workpiece. You are doing the machining. As you increase the cutting velocity, the cutting cost become decreases because per unit time now you are number of units, so that's why cutting cost get reduces. Meanwhile the wear of the tool maybe increases, so the tooling cost or the repair cost is going to be what in. Now if you are going to add up both the thing, if you are going to add up both the thing, then it will give you, my dear, it will give you what? It will give you the total cost. What? This is the total, right? This is what? This is the total, this is the total, okay. So this total cost we are obtaining minimum at some particular velocity. This is the optimum velocity, the optimum cutting velocity, cutting velocity, optimum cutting velocity where you are getting total cost. If you are getting total cost what? So overall you can write what? Overall we can write that the total cost, the total cost will be equal to what? Will be equal to your cutting cost, your cutting cost, right? Your cost plus tooling dot tool. Now we want to know that velocity, we want to know that optimum velocity, okay. We want to know that optimum velocity where we are getting total cost minimum. So we have to differentiate that total cost with respect to what? With respect to cutting velocity, and put it 0, you will get that velocity. Now you don't have to undergo the derivation. How can we get the total velocity? You have to remember the velocity, right? Once you find out the velocity, actually what we do, this is the topic of what? This is the topic of what? This is the topic of your tool life. So my dear, you have to find that tool life. You have to find that tool life. You have to find that life which is corresponding to optimum cutting velocity, corresponding to optimum cutting optimum cutting velocity, okay, which give the total cost, right, which give the total cost what? Minimum. The basic is same. Differentiate the total cost with respect to your cutting velocity, you will get. Now, that tool life will be what? That tool life will be TC, that is tool changing time. Suppose that if the tool is fail again and again, that you unmount the tool from the setup and you do the regrinding and again you mount. So that is what? Tool changing time, right? So TC, tool changing time, plus CT. CT is tool repairing cost divided by CM. CM is machining cost into 1 minus n divided by n. So let me write down what is CT. Okay. Before that, once you know the T naught from that equation, meanwhile, I will write down the meaning of every individual parameter, my dear. Here, T naught, this is what? This is the optimum tool life, right? Now, that TC is what? TC is tool time, tool changing time, tool changing time, and it should be in. Now what is tool changing time? I told you that tool changing time is that time when the tool get wear out, you are going to unmount the tool, and after repairing you are going to mount the tool. That is tool changing time, right? uh CT is what? CT is the tooling cost. CT is what? Tooling cost, might. Is what? Tooling cost. And the unit of the tooling cost is what? That is rupees per service, right? Always remember rupees per service. The how can now sometimes student can ask me, sir, how can we find out, how can we figure out about the CT? My dear, whenever you get the unit rupees per service or rupees per replacement, the unit is rupees per service, and it is a CT, that is a tooling cost, right? Now again, CM is what? Machining. CM is what? Cost, right? What? Machining cost, and the unit is very simple, that is your rupees per minute. Okay, rupees per minute, my dear. A cost which has a unit, my dear, a cost which has a unit rupees per minute, that that cost is what? That cost is your machine. And this is the thing. Now once you get the optimum tool life, this is the optimum tool life. What is a T naught? T naught is the optimum tool life, right? What is a T naught, my dear? Let me write down the T naught. T naught is what? Optimum tool life for minimum cost, right? T naught is what? T naught is not is what? T naught is optimum tool life, optimum tool life, optimum life for minimum cost, for and the unit should be in. When you put, when you find out the value of T naught from that equation, then use not T naught to the power n equal to C. T naught here you get that optimum velocity, can get that optimum velocity, right, where you will get the total cost, right? So this formula is very important. Please remember this formula. Right? Please remember this formula. This formula is very important. Right? Please, this, right. Now the next formula, generally which comes in economics and metal cutting, that is your optimum tool life for maximum, right? Optimum tool life for maximum productivity. So let me write down optimum tool life, optimum tool life for maximum productivity, maximum dark T, right? Optimum life for maximum productivity. So my dear, this is basically we are going to figure out that tool life, okay, which is corresponding to that velocity where we are getting maximum production rate, right? Maximum production rate. It means what? You can write maximum production rate means what? Minimum production time. Minimum production time. Production, production, right? Minimum. Now, my dear, please write here. So this tool life is that optimum life is equal to TC, right? T 1 minus I n. Here the meaning of T n is the tool changing time and it's the exponent. Now, once you get that tool life, use this equation T naught to the power n. Put here, get that velocity where your maximum, where where you get the maximum production rate, maximum rate. Is that point is clear to everybody? Is that point is clear to everybody? Is that formula is clear to everybody? Yes or no? Tell me. Is that point and formula is clear to everybody? Yes or no? Okay. Now I'm going to give you one more graph, that is the minimum cost versus production, right? Minimum cost versus production cost versus, so cost versus cost versus rate, right? Minimum cost versus, my dear, let me draw the graph. That graph is very right. That graph is very important, and the graph is what? Simply see this graph. The graph here. Now this is what cost versus cutting velocity versus cutting velocity, right? This is production rate versus cutting velocity versus cutting velocity. Now, this is what? The graph of total, the graph of what? This is the graph of, right, and this is a velocity where you are getting the velocity where you are getting the minimum, right? Where you are getting the minimum, you are getting, my dear, right? This is the velocity, right? This is the velocity. We call that velocity is optimum velocity. Now, draw the another graph, and that graph is like this is production rate versus cutting velocity. If you are increasing at this, my dear, so this is the velocity at which are getting the maximum, maximum, right? Maximum. Now your profitable working range, your profitable working range must be in this region. Your profitable working range, right? Your profitable working range must be in profitable working range. Basically, your profitable working velocity must be lie in between that. What? You always remember that optimum B maximum profit, right? Your working velocity, velocity at which you get the maximum profit will lie in this, right? Will lie in this. Okay, P max production. Please always have this relation and graph. It is a very important, right? It is a very important parameter, right? It is a very important parameter. Now, so I hope this point is crystal clear to everybody. If is there any doubt, you can ask, right? Now let's move to numerical. Uh, can you try this numerical, please? Try this numerical. Yes, hello, everybody. Can you try this numerical? Will you try this numerical? Okay, so I'm going to provide some time so that you can try this by yourself. Here, your time starts now. Yeah, tell me the answer of this question, please. Tell me the answer of this question. Tell me the answer. Yes, yes. Okay, I will try. 1 minute is over. Will you try one more minute? Will you try this question for one more minute? Will you try this question for one more minute? Yes, dear. After I will solve this question. Right. Then after I will. Yes. Yes. 10 seconds left. Seconds left. 10 seconds left. 5 seconds left. Okay, I will try this. Right. See in this question what is given to us here. Parameter. There are two and let's say one. The exponent of two one is, let's say n is 0 point and constant k is given really for tool 0.3. So the cutting speed above which a will have a higher tool life than tool B, right? The condition us, right? Us idea. Now we know here we know that the power n equal to, or you can write that in, can write that here k, here k the power 1. In both the case velocity is, in both the case the velocity is, right, have to keep velocity, and we have to find that velocity above which the tool life a is greater than tool life 2. So my dear, here you can write that equal to what, a1 divided by v the power by n, on you can write that t2 equal to what, by v 1 by, right. Now put the value here. Now put the value here. So k1, right, divide by v the power 1 by n equal to k2 by v 1 by n. My dear, k1 is what? K1 is here v 1 by n, what, 5 greater than equal to, okay, 60 divided by 1 by and, right. So this is the thing, right? This, Now, if we solve this thing, 95 v point 3, we are going to solve the inequality. We have to remove the right, 5 v point 45. Solve this, you got 20 meter per the final outcome. This is the final what? This is the final answer. Yes, yes, please. If the Taylor's two life exponent is 0, start the watch. Yes, solve this question. Yes, please solve this question. Yes, yes. Yes, please. Okay. So here your 1 minute is over. So what is the given in this question? Given that n, that is 0, right? Okay. And the tool time 1.5. The tool life in for maximum productivity. If you that the tool life for the maximum, right, will be what? 1 minus 5 and 1.1 minus divide by with the value of what? Your so 1.5 in 1.5 in 1 minus it or t what, right? The answer. Now one more question we are going to start down the question. Let me write down in an orthogonal or in a machining operation. Right. The tool life obtained is the life obtained obtained 10 10 minutes. The tool life obtained is cutting is at a cutting is at a cutting 100 meter per right 100 meter while at 75 meter per minute while at 5 meter per right cutting speed while at 75 meter per minute. Okay, the life the tool life is life is okay the tool life is right the value of index the value of index value of index the value of index have to find out. Okay, the value of index in the Taylor's tool Taylor life life. My dear, here the machining is same. You can write that what 100 the power n what 5 what 30. Now will you solve this? Will you solve this, my yes? Take the log on both the side, right? So 30 by 100 100 divided by 7 the power x all equal. Get the value of n. Tell me value of what is the value of n? What is the value of n? Tell me. I think it will be point if I'm not wrong. Yes. If I'm not wrong, then the value of n will be 0 point. Okay. The value of n will be 0 point what? 26. Yes. What is the value? Yes, Rajesh Sharma. 0.26. The value of n will be what? My dear, if you are looking this chapter for the gate or some numerical purpose, then this stuff is okay, sufficient for your gate point of view, right? So I hope you understood today's lecture. Tomorrow we are going to play and we are going to start. Thank you very much for watching this video. We are going to tomorrow. Good night. Take care.